This is my Physics 2212, Lab 5 on magnetic molasses. So an introduction to this lab, the purpose was to make sure the length of time, or to measure the length of time it takes a bar magnet to fall through a foil tube and create a computational model of this occurring and compare the results. So a preview of the result, the physical experiment resulted in drop times of 1.283 seconds, and the model computed a much longer time of 7.514 seconds. So some models and fundamental physical principles used in this lab, we have Faraday's law, the Biot-Savart law, Newton's second law, and Newton's third law, which states that every action has an equal and opposite reaction. We have or in this case, forces. We have a magnetic force on a loop, and the time derivative of flux from a dipole. So the lab procedure, we had a system of the bar magnet and aluminum tube and surroundings of the hands holding the tube and magnet, the air, anything else in the room, and so for the experiment, we determined which end of the bar magnet was north and marked it. We took the foil tube and held it vertically and then dropped the bar magnet through the tube 5 times, recording each time, or we actually did 6 times. And then we used a video scrubber to determine how long it took the magnet to fall from top to bottom each time. Here is my lab partner performing the experiment. And then we took the average of those results, which as you can see is 1.283 seconds. So some possible error sources. We have that one trial used a slightly different camera angle. The time was only calculated to the 10th of a second. The tube may have been held in slightly different positions. Air resistance is assumed negligible. And then in the code, we have the previous dipole moment was used, which was calculated in a different lab and could be wrong. And it probably is, as we will see. And the magnet used for this experiment could have a slightly different strength from the one used in the previous lab. So some checkpoint questions. Why can't we use a ferrous tube? That's because iron has strong magnetic properties, so a ferrous tube would create an induced magnet in this experiment. And then what happens to the magnet and how does it compare to what would happen in free space? It falls slower than it would in free space due to the force being acted on it in an upward direction. So the glow script modeling, here we're just initializing the tube and the magnet. Here we are we're calculating the flux through the magnet, flux through the a ring. And here we're finding the gravitational force on the magnet. Here we're iterating over each loop in the ring to first find the flux on it, or flux through it, and then calculate the induced current through it. And then here we're finding the magnetic field at the ring. And then here we're finding the total force, gravitational and magnetic, on the dipole magnet itself, or the bar magnet itself, and then here we're updating its position. So some results in discussion. As you can see, this simulation took over 7 seconds, which is not accurate, obviously. But some questions to answer here. The from above, the red, not shown in the screenshot, but in the simulation you can see it, goes counterclockwise and blue goes clockwise. For the induced current, what happens to the dynamic of the system when you flip the magnet around? Nothing would really change other than that the direction of current would then be in the opposite direction. How does the total time in tube of your real-world system compare to that of your computational system? Well, for this, obviously, we can see that 7.5 is a lot more, and the reasons for that were explained back in the error slide. And then what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? We can see that the forces were unequal at the start and end of the time as the velocity increases and decreases, and that they were approximately the same throughout the middle of the time that it was in the simulated tube, because the velocity stays the same. So what if the resistivity were much lower? The induced current would be much stronger, and the upward force on the magnet would be much stronger. If as close to 0 as possible, the magnet would stop moving. If holes or slits were cut in the conductor, the current induced in the tube would be disrupted, reducing the upward force acting on the bar magnet and causing it to fall faster. Thank you.